In this video, we will continue our discussion of describing solutions as being acidic, basic, or neutral, and our pH scale. So we talked previously about describing something as being acidic, basic, or neutral based on the concentrations of hydronium or hydroxide. Another way we can describe acidity is using something called the pH scale. The pH scale is a log scale based on the hydronium concentration. We use it to simplify numbers normally expressed in scientific notation. So if we think about those numbers that we saw with the hydronium and hydroxide concentrations, 10 to the negative 7th, we tend to not like to have to deal with numbers like that. So we simplify it, and log scales are the way that we can do that. And so we're going to define pH as being the negative log of the hydronium concentration. This takes that scientific number and converts it into a much simpler number that we can use to very quickly judge acidic, basic, or neutral. Now we've got to be careful here with significant figures. When we're dealing with logs or natural logs, the significant figures appear in the decimal only. That's because the number before the decimal is based on your exponent. So if the number we're taking the log of has 3 significant figures, then our answer has to have 3 decimal places. And we'll look at examples. So pH is a negative log of the hydronium concentration. We need to be able to go back and forth between pH and concentration. So concentration of hydronium will be equal to 10 to the negative pH. pH simply gives an indication of the hydronium concentration. That's all it does, is lets us compare relative concentrations. Now we have a typical range of 0 to 14. This is not set in stone. This is just your average range. We can have numbers above 14. We can have numbers below 0. Now, if I had a hydronium concentration of 1 times 10 to the negative 14th, if I go to my calculator, I plug that number in, I take the negative log, I'm going to get a value of 14. Here's where our significant figures become important. My concentration here has 2 significant figures. My pH here, that 14, is coming from that exponent here. So it's not a significant figure. My significant figures are coming here in these decimal places. So since my concentration has 2 significant figures, my pH needs to be taken out to 2 decimal places. So just stating 14 would be incorrect. We need 14.00. If my concentration was 1 times 10 to the negative 7th, my pH is going to be 7.00. If my pH or my concentration is 1, my pH is going to be 0. Now remember that when we talked in terms of concentration, if I had a hydronium concentration equal to 1 times 10 to the negative 7th, then that was going to be a neutral solution. That's corresponding to a pH of 7. So on our pH scale, pH of 7, exactly 7, is going to be neutral. Now, if my hydronium concentration was greater than 10 to the negative 7th, so anything larger than 10 to the negative 7th, that was going to be acidic. And so between 7 and 0 on my pH scale, we're going to look at acidic. And then if my hydronium concentration was less than 10 to the negative 7th, that was because the hydroxide was greater, and that was going to be basic. So, in terms of describing our solutions, a neutral solution has hydronium equal to 1 times 10 to the negative 7th, so a neutral pH is 7.00. An acidic pH is going to be any pH less than 7.00. And again, that's because it corresponds to hydronium concentrations greater than 10 to the negative 7th. A basic pH is going to be any of my pHs greater than 7, because that's going to correspond to smaller hydronium concentrations and therefore greater hydroxide concentrations. What we find with concentration and pH is that they are inverses of one another. As my hydronium concentration increases, my pH decreases. So smaller pHs mean larger hydronium, larger pHs mean less hydronium. Now, we also have what's a pOH scale, because remember we have both hydronium and hydroxide present in our solution. So pH is based on the hydronium concentration. If we want to focus instead on the hydroxide concentration, we use what's called the pOH scale. Just like the pH scale, it's a log scale. This time it's based on the hydroxide concentration. We're going to define pOH as being the negative log of hydroxide, and therefore the hydroxide concentration is 10 to the negative pOH. These scales are opposite because remember in solution what happens to the hydronium, the opposite's happening to the hydroxide. No matter what scale we're on, neutral is going to correspond to 7. So on the pOH scale, the pOH is 7. That's neutral. Acidic pOH is going to be pOHs greater than 7, and basic will be pOHs less than 7. So again, smaller pOH, that's going to mean larger hydroxide concentration, so more basic, and the larger the hydroxide concentration, the smaller the hydronium concentration. So we've got a bunch of relationships we've seen so far. So we've defined pOH. We have a relationship between pOH and concentration. We've defined pH, and we have a relationship between pH and concentration. Now also remember that that whole equilibrium in water is described by Kw. And Kw is the concentration of hydronium times hydroxide, which equals 1 times 10 to the negative 14th. Now we could do some derivations or some rearrangements to our equation. If we were to take the negative log of each side, we would get the negative log of hydronium times hydroxide equals negative log of 1 times 10 to the negative 4th. We rearrange using some log rules. We get the negative log of hydronium plus the negative log of hydroxide equals the negative log of Kw. If I take that negative log, that gives me 14. Anytime we take the negative log of something, we're going to represent that with a lowercase p. So lowercase p just means take the negative log. So this equation becomes our pH plus our pOH equals 14. So we've got a whole bunch of tools that we can use for calculations. So we've got pH equaling the negative log of hydronium. We have hydronium equaling 10 to the negative pH. We have pOH equaling the negative log of hydroxide. We have hydroxide equaling 10 to the negative pOH. And then we have pH plus pOH equals 14. And we have Kw equals hydronium times hydroxide. This is our toolbox that we can use to pull from in order to solve problems. So looking at problem number 10 here, we're asked to calculate the pH of a 6 molar hydrochloric acid solution. So if I want pH and I have concentration, we're going to set this such that pH equals the negative log of that concentration. So my pH is going to equal negative 0.78. Now remember that pH scale went from 0 to 14, but we said it's not set in stone. So here I have a pH less than 0. This is possible. And a 6 molar solution of hydrochloric acid, that is a very common solution. You guys have worked with this concentration in lab. It's a very high concentration of hydronium. Now we need to be able to use our toolbox to convert between any of these things, between pH and hydronium, POH, and so on. And we need to be able to use these to determine if solutions are acidic, basic, or neutral. So here in problem 11, we're asked to calculate the hydroxide concentration, the pH, and the POH in a solution in which hydronium equals 0.35. And then we're asked if the solution is acidic, basic, or neutral. Now we can answer that last part before we do any calculations. I have the hydronium concentration. It's 0.35. If that concentration is greater than 10 to the negative 7th, it's acidic. Now we can use this to check all of our answers, check our math, because all of our answers should agree with defining an acidic solution. Now we need identification of being acidic in order to check all of our math, because all of our answers should agree with being acidic. Now we can do these calculations in any order. I'm just going to start with pH. And so if I want pH is going to be the negative log of my hydronium concentration. So negative log of 0.35, which gives me a pH of 0.46. Checking to make sure things make sense. If I have an acidic solution, then my pH should be less than 7. 0.46 is less than 7, so my pH makes sense relative to our previous determination. Now we also need hydroxide's concentration, and we need a POH. And we can do this a number of ways. One way we can do this is we can use our relationship here between Kw, hydronium, and hydroxide. I can take that Kw equation and I can rearrange it to solve for my hydroxide, so that my hydroxide equals Kw over my hydronium. Kw is a constant. It's 1.0 times 10 to the negative 14th. My hydronium concentration was 0.35. So I'm going to get a hydroxide of 2.9 times 10 to the negative 14th molar. Again, checking to make sure things make sense. In an acidic solution, hydroxide should be less than 10 to the negative 7th. So here I definitely have something less than 10 to the negative 7th. This represents an acidic solution. And then the final thing we need is our POH. I have the hydroxide concentration. I could take the negative log of that. Or I have the pH, so I could use my pH plus my POH equals 14. So if I do that and I rearrange my equation, my POH is going to be 14 minus my pH of 0.46, so that my POH is 13.54. Again, checking to make sure things make sense. On the POH scale, POHs larger than 7 are going to represent acidic solutions. Now, next we want to calculate the hydronium concentration for a sample of orange juice with a pH of 3.805. So again, we had that toolbox that we could pull from, and one of them had a relationship between pH and the hydronium concentration. So we had the equation that the hydronium concentration was going to be equal to 10 to the negative pH. So we would have 10 to the negative 3.805, which is going to give me a concentration of 1.57 times 10 to the negative 4th molar. Now remember, we brought up significant figures. My pH, even though it has 4 digits, the decimal places are only 3. So there are only 3 significant figures here. So my concentration should have only 3 significant figures. Now we can go back to our previous problem and talk about significant figures as well. So in this problem, problem 11, where we had the hydronium concentration was 0.35. we had two significant figures. When we take the negative log of that value, we need to make sure that we have two decimal places to represent two significant figures. My POH should have two decimal places, and then my concentration should have two significant figures. So our remaining problems, we're going to continue to do the same thing. We're converting back and forth between these values. Here we've got the hydronium concentration, and we're asked to calculate the hydroxide. And in part B, we've got hydroxide, and we're asked to calculate hydronium. So they're all related through that KW equation. So hydronium times hydroxide, and that equals 1 times 10 to the negative 14th. So rearranging that equation, if I'm looking for hydroxide, hydroxide is going to equal KW over hydronium. So 1 times 10 to the negative 14th divided by 2.5 times 10 to the negative 4th, which will give me a hydroxide concentration of 4 times 10 to the negative 11th molar. Now, if I have hydroxide and I'm looking for hydronium, I can rearrange my equation. My hydronium will equal KW over hydroxide. So 1 times 10 to the negative 14th over 1.5 times 10 to the negative 3rd. That will give me a hydronium concentration of 6.7 times 10 to the negative 12th molar. And then finally, problem number 14, we're asked to calculate pH. So in part A, we have hydronium. If I have hydronium, my pH is just the negative log of that concentration. So I'm going to get a pH of 9.662. So again, considering our significant figures, my concentration here has 3. So my pH here needs to have 3 decimal places. Now for part B, we're given POH, and again we want pH. So we know pH and POH are related through the equation that pH plus POH equals 14. So rearranging, my pH equals 14 minus the pH. Sorry, minus the POH, which is going to give me a pH of 8.26. And then finally, part C, we've got a hydroxide concentration. There's one of two ways we can solve for this. We want pH. pH is based on hydronium. So I could solve for the hydronium concentration using my KW equation and then take the negative log. Or I could take my POH. So my POH will be the negative log of 12, which would be negative 1.08. And then my pH would be 14 minus that value. It's just going to give me 15.08. So again, we've got a number of relationships. We don't have to worry about memorizing those relationships, but we've got to be able to grab them from our toolbox and use them properly. So we've got to be able to look at which equations will fit our needs.